Hello and welcome to Sets Sheet 5 from my Formalising Mathematics 2022 course. And the exciting thing that we're doing here that we weren't doing before is that we're talking about equality of sets. And there's two problems that used to be on Sheet 2. Eagle-eyed viewers who watched the video for Sheet 2 will have seen the fail in there. So how do you prove that two sets are equal? The idea is two sets are equal if and only if they have the same elements. Two sets are equal if and only if, I should speak more clearly, right? Two sets are equal if and only if they have the same elements. And so we can use the extensionality tactic because that says exactly that. So there it is. We've got to now prove that x, a random element of x, is in A union A if and only if it's in A. And I guess we should probably split it. So now this first one, we could do rintro. What could we do? This HA or HA, comma. Oh, I don't like the errors everywhere. Let's sort out the errors. Let's put a comma there. That should be okay. So now we've got two goals again, and this is exact HA, and this is exact HA there. So what's going on is that we know that x is in A union A, so that means x is in A or x is in A. So we have to deal with both cases, slightly ridiculously. And funnily enough, both cases have the same. Oh, do you know when you have to? Oh, there is something we could do here. That rintro tactic gives us two goals, and the proofs are exactly the same in both cases. So we can put a semicolon there, and then we only need to write it once. There we go, a little semicolon. After that semicolon, it means do the next tactic to all the goals. So in fact, we don't even need it in brackets anymore. There. So that's one way, and then the other way is intro H. No. There we go. Intro H, and now what? I've got to prove that x is an A union, so that's an OR, so I can either go left or right, right? I'm going to go left or right. Which way shall I go? If I choose one or the other, will the proofs be the same or different? That's kind of an interesting question. In fact, I'll tell you the answer to that question. Let's go nuts. Let's do definition left proof. Let's go left there, and now I've got to prove. So this is exact H, right? And now let's do the same thing here. Let's make the right proof. The error is you've already got something called left proof. Yeah, that's all right. I'm going to change the name. Right proof. Now let's go right. So there we go. Now we've got two proofs of A union A is A. So we could check left proof. Left proof says if X is a type and A is a subset of X, then A union A is A. And we could check right proof. And right proof is a proof of the same thing. But the two proofs are very slightly different, right? One went left and one went right. And so are those proofs the same, or does it make sense to talk about proofs being the same? So let's see. We could do example. We could do left proof. You see, check tells you the type of a term, right? Left proof is a proof of that statement there. So left proof is a term of that type, and right proof is a term of the same type. If I pull this over here. And then start moving my cursor around, you can see left proof and right proof, they've got the same type, so it makes sense to ask if they're equal. So example, we can ask if left proof equals right proof. There. So are those proofs equal? Is that goal solvable, right? Is that goal solvable? Are those proofs? Yeah, are those proofs? I mean, how does lean work? So in some theorem proof, my understanding, I know very little about homotopy type theory and these other theorem provers, but my understanding is that in some theorem provers, these proofs would not be equal. But in lean, these proofs are equal. And furthermore, if I'm right, I've gone rather off script here, so this all might go horribly wrong. If I'm right, there you go. REFL proves that those proofs are equal. And that's because more generally what's happening in lean, if I have example, if P is a proposition, so you might kind of think, well, they're pretty much like, you might sort of accept the fact that those proofs are equal because they were pretty much equal, because like A union A is, I don't know. You might convince yourself that those proofs were more or less equal anyway. But let me show you something even more general. If I've got an arbitrary proposition, and then I've got H1 and H2 are both proofs of P, I claim that H1 equals H2. There. And I claim the proof is REFL. So this turns out, I don't know why I'm telling you this. This is supposed to be a video about something completely different. It's basically an axiom in lean that any two proofs of a proposition are equal, and furthermore they are equal by definition. And some people who study proof theory wouldn't think that at all. And basically the moral of that story is, if you're studying proof theory, then you probably shouldn't be using lean. You should be using another theorem prover. But if you just want to get modern algebraic number theory done, you know, the kind of thing that I'm interested in when I've got my number theory research hat on, then it turns out that lean is quite a useful tool for this sort of thing. So, you know, sort of worrying about technicalities like this, that worrying about whether two proofs are the same is sort of an interesting mathematical question, but it's sort of not relevant to trying to prove theorems in the Langlands program. And so I don't care that lean thinks that two proofs of a proposition are always by definition equal. Right, now let's get back to the script. Let's change that to an example. Now let's get rid of this. In fact, this is, I don't know why I'm waffling, because this is a huge problem sheet. What am I doing? A intersect A, right, back to the point. A intersect A is A, so x to x, and then, oh my goodness, I mean, dear, does simp work? You see that these things are, I mean, we could do it that way. Let me squeeze simp, there we go. Squeeze simp tells you the lemmas that simp uses, and it used inter self, there it is. So in fact it's exact inter self A there, and there's no point doing begin exact end. You can just get rid of the begin and the exact and the comma and the end, and you can just do that there. Sort of found with squeeze simp. A intersect, I mean, I bet simp does them all actually. There we go. I mean, let's do some of them. Let's do this one. X, I'm supposed to be teaching you about X. Let's learn about X, because that's what we're supposed to be doing. And now I've got to prove that X is in A intersect the empty set, if and only if X is in the empty set. So I think I've got to split it. And so now I've got to prove, so now this one here, so sorry. This first goal, I'm going to do rintro, and then I can do this. You see, I can do H, X, H, emp. There. And now I've got to prove, you see, I did an intro. The intro was an and statement, so I did an intro, then I did a cases on the and statement. But H, emp, this is definitionally equivalent to false. And so I could just do this probably. Does that do it? There we go. It's lovely. Not often you see a goal solved with rintro. And this way as well, I could just do rintro, nothing at all, right? The point is, X is in the empty set is already false, and if you have a false hypothesis, you can prove everything by doing cases on it. A union univ is univ, so the simplifier does it. This one here, the simplifier. No. This one I'm going to have to do some work. Right. Let's do this one. This one looks like a nice one to do. Intros HAB and HBA, and now I've got to prove that A equals B. So this is a good one to use X on actually. X. So now I've got to prove that X is in A if and only if X is in B. And if I split it, then you see I've got to prove that X is in A implies X is in B, and I've got to prove that X is in B implies X is in A. And that's exactly what HAB and HBA are, right? So this is probably exact HAB, is it? Or do I have to feed it X? Yeah, no, it works. There we go. It's probably worth telling you what's going on here. So let's switch notation off. Set option pp pp.notation false. That's it. And now you see everything looks terrifying because we're not using any notation. This arrow is somehow inbuilt lean. This is some inbuilt pi type that's a primitive of the language, but we're not using any other notation here. And if I unfold has subset dot subset, which is apparently, you see, we saw this subset symbol here. Oh, it's unfold it. No, what? Oh, at I see. At HAB. If we unfold that thing at HAB, then it says a dot subset b. So that's also, the type of A is set. So we have to fold set. Let me talk you through this. A dot subset b. A has got type set x. So a dot subset b means set dot subset ab. So let's keep going. Let's unfold set dot subset. There. And now are we there? Yeah, there we go. And so HAB, so now you can actually see, so now we can switch notation back. Let's put notation back on again. And now you can see this is the actual definition of A as a subset of B. And it says, for all A, if A is in A, then A is in B, as I told you earlier. But what I didn't tell you was that, in fact, in the definition, that A is in these squiggly brackets. And the squiggly brackets means, oh, Lean's going to work them out. Like, don't worry, Lean's going to work them out. You don't have to tell me what the input is. But I really wanted to tell Lean what the input was. I suspect that apply HAB would have worked. Yeah, apply HAB works. But if I want to do exact HAB, then I'm going to have to tell it what the input is. And so you can put an at in front of it, because the at overrules all the brackets. The at just says, okay, Lee, I'm overruling your decisions on these inputs. I'm going to apply them all myself. And so so similarly, this goal, of course, here will be exact at HBAX there, and that's finished the proof. And you don't need the unfolds; those are just to work out what was going on. And that means now that because we don't need to do the split, we can just do this exact pointies at HABX, comma at HBAX. There you go. So there's a proof of that. I mean, that is definitely in the library. That I even know what it's called. It's like exact set dot subset dot antisim or something, isn't it? Is it that? There you go. Why? What? I thought I did that. Didn't I do that? Oh, I did simp. Anyway, could have done library search. But anyway, there's a nice 3-line proof. So library search works. I see. Yeah. So simp might not. Yeah, you see, simp doesn't work for. Why doesn't simp work for that? That looks pretty simple. That should be a simp lemma. That would be a disastrous simp lemma if you think about it. Because the idea is that the simplifier is supposed to when you have a simp lemma, the left-hand side is supposed to be more complicated than the right-hand side, and that's not the case here, right? The sides are kind of equi-complicated, right? It's not any clear that one side is simpler than the other. So that would be a disastrous simp lemma. If that was a simp lemma, then it would just fire. If the moment you had an A and B. The moment you had a random goal with an A and B in it, if you ran simp on it, it would change A and B to B and A, and then it would change B and A to A and B, and it would just sort of keep going forever. I think actually Lean simplifier is slightly cleverer than that, and it might not go on forever. But in general, you can see why you're treading on sort of dangerous ground. But I bet library search works. It's going to be called set intercom or something. Yeah, intercom. So that would work. There, sort of found with library search. And okay, let's go get. And that's going to be called exact into a sock, A, B, C or something. It's not. No, it's not, because into a sock is apparently the other way around. So we could apply the symmetry tactic, which switches. Do you see what symmetry changes the goal A equals B? It changes it to B equals A. And there we go. So that wasn't found with library search. I guessed the name. There. And that one's going to be whatever. I mean, maybe I'll do. Do you know? Well, I'd actually solve one the way they're supposed to be solved. I mean, just you can see. You see, I've done too many of these things, right? Oh, this is just so long. Okay, let me split. So what's this one? Rintro, open brackets, HA or HB or HC. Is that right? Yes. I think actually, if I do, yeah. Anyway, Rintro. There. Now I've got 4 goals. Terrific. And this one is left. Left. The unions are just ors, you see. So you have to go left and right. Left assumption. That's that one. So after the split, this should all be like this, shouldn't it? And now Lean's totally confused. Let me close that bracket and put a comma. Then it should be great. Now we're back on our feet. And that one is going to be left, and then right, and then assumption. There. So it's a case of sort of steering through and then right assumption, presumably. Yeah. So that's kind of interesting. That union is left associative, which is quite rare. I wonder why they did that. I genuinely don't know why they did that. Let's have a look at the goal. Yeah. You see, I put the brackets in specifically in the statement of the lemma, but Lean has dropped the brackets here. You can see A union B highlights, and A union B. You see B union C won't highlight, which is sort of slightly surprising because I think addition. I mean, I just go crazy. Example: 1 plus 2 plus 3. 1 plus 2 plus 3 equals 1 plus 2 plus 3 colon equals. Sorry. And now let me look at the state. Yeah, see. Yeah, so I am in fact just going crazy. I am going crazy, and everything is left associative. Yeah, okay. Right. So there we go. I've finished going crazy now. I'll get back to the. I'll get back to this. So Rintro. Oh, so now we've got to be careful. So because this is going to be something like this, HA or HB. That's right. These brackets are. I know what I'm confusing myself about. These brackets are right associative. The Rintro brackets are right associative, but the operators are typically left associative. Yeah. So when the IC, okay, back to normality. When the brackets are there, you don't need extra brackets in the Rintro. But here the brackets are not there. I'm introing A union B union C with no brackets, and then I need brackets with the Rintro. Honestly, why do these computer scientists make up their mind? Now what are we doing? So this is going to be left assumption, and this one is going to be right left assumption. Maybe I should just go through what's going on here. I've got to prove. So if I go, I've got to prove that either X is in A or X is in B union C. And if I go right, it reduces the goal to X is in B union C. And then I go left, and the goal is reduced to B. And then here, this one is it's going to be right assumption. Does that compile? Yes, that compiles because I have no errors. And then this one, I mean, honestly, it's going to be cool. So here's a question. Will that be in the library? Because it's just some random statement about unions and intersections, right? Is that going to be in Lean's maths library? And I say, yes, it is, because it's a really natural assertion about unions and intersections. Like if you if that union was a if A, B, and C were numbers, and that union was a multiplication sign, and the intersection was an addition sign, then it would say A times B add C is A times B add A times C, right? Which is distributivity. That means if you change all the unions to timeses and all the intersections to pluses, then this becomes distributivity of times over plus. So I bet this will be in the library because it's a natural distributivity statement, and it will be called something something distrib, like union into distrib or something. Let's see. It's called, it's not there. It might be there. It is there. There you go. Union distrib left. I was a bit worried for a minute there after that build up because library search took a long time. And so, is this, so what's this? Is this exact inter distrib left or something? Is that there? There it is there. But it's not true. A, B, C. Bingo. So what's inter distrib right? That's an interesting question. Have H colon equals inter distrib right, A, B, C. Oh, of course. Yeah. We're doing A times B add C, but the other thing we could do is B add C times A, right? B add C times A is B times A add C times A. So there you go. So thanks, library search. I guessed what this was called. Was called on the basis of previous answer. And there you go. That video didn't go remotely like how I thought it would go, but I hope you learned something from it anyway. Thanks for watching.